We are continuing our discussion on estimation of fundamental matrix, and in the last lecture we discussed how the equations can be formed using the pairs of corresponding points in relation to the elements of fundamental matrix, and by solving those equations you can get those elements of fundamental matrix. One of the things we are discussing that we require to perform coordinate transformation as the dynamic ranges of coefficients of those equations, they widely vary because of the nature of the equations. So, we will continue that discussions, and as we discussed that we will map the coordinate points to these ranges, bring them into these ranges. An example is shown here. Usually that is a very common case that image coordinates vary between say 0 to 700 in this example and 0 to 500. There are other values. This is a typical range, and there you can see product of those coordinates will have a very large dynamic range compared to single variables of coordinate points, single points. So, the example of a transformation will convert these coordinates into these ranges is given here. You can see that this transformation is given in this form, that if I multiply this matrix with x prime. So, I will get the transformed point. So, let me denote the transformed point as say x t, say x t coordinate, that means that should be equal to 2 by 700 x minus 1. Similarly, y t is 2 by 500 y minus 1, and the scale factor remains 7. So, given x y, we will be converting this into this value. So, that would translate the origin to 0 0 in the middle of this minus 1 has this effect. Anyway, as discussed that you have to apply the corresponding computations of to apply that transformation back into what you get as a fundamental matrix out of this computation, then the inverse transformations are to be applied to get the original fundamental matrix in the respective coordinates of the image planes. We will now continue, we will see what other aspects are there. So, as we mentioned that this is a paper where actually this particular technique is discussed, and it has been shown that least square error method yields good results when we perform this transformation. So, now we will consider the other aspect of this estimation. I mentioned that in the previous case that we have not applied the constraint of singularity on the fundamental matrix. So, the solution what you get, that is not truly giving you a fundamental matrix unless it satisfies that singularity constraint. So, how to enforce that singularity constraint? So, that is what we will be discussing here. So, here you see that this constraint is expressed in the form of that the determinant of the matrix F should be equal to 0, and also we know that maximum rank of F could be 3, since it is rank deficient. So, it should be less than 3, and in this case it would be 2. So, there is 1 0 particularly of this fundamental matrix. We discussed also that there is a epipole, that is a left epipole in the reference image, reference plane, image plane, that is a 0 of this fundamental matrix, that is the right 0. Similarly, there is a left 0 which is the right epipole. Now, if I perform singular value decomposition of a fundamental matrix, So, we represent singular value decomposition in this form. So, you see that U is a matrix which is orthogonal, or you can make it also orthonormal, which means if I take the column vectors. So, let me represent U as a set of column vectors in this form. These are vectors, I will use these notations. So, each vector is a column vector which is of 3 cross 1 dimension. That means, U is a 3 cross 3 matrix. And in a singular value decomposition, all these column vectors would be orthogonal, or you can make it orthonormal also, as I mentioned. Similarly, V is also another matrix, 3 cross 3 matrix, whose column vectors are also orthogonal. So, you have V 1, V 2, V 3. So, this is also orthogonal. So, any square matrix or even any matrix, not only square, can be decomposed into this form, into this particular structure using singular value decomposition. So, in this case particularly I will discuss with respect to square matrix only in this context. So, it can be decomposed into this form. So, U, as I mentioned, 3 cross 3, then there is a diagonal matrix, and then V, which is also a matrix, but no, you have to take transpose of this V. So, I can write also like U 1, U 2, U 3, and this diagonal matrix, there in this case it is also a 3 cross 3 matrix. You can see that if I multiply, I will get a 3 cross 3 matrix. So, diagonal matrix, as you know, that all off diagonal elements would be 0 except the diagonal elements which should be non-zero, not necessarily that it should be non-zero, it could be 0 also. And we can apply sign laws, etc. We can adjust the signs in both the sides, so that we can make it all positive. We can rearrange the, let me write here. So, I will be writing V transpose as V 1 transpose, V 2 transpose and V 3 transpose. So, these are the corresponding row vectors of V, which is transpose of these columns V 1. So, this is the form, and through matrix expansion, submatrix multiplications, we can see that this can be represented as U 1 sigma 1 V 1 transpose plus U 2 sigma 2 V 2 transpose plus U 3 sigma 3 V 3 transpose. So, that is what is written here also. And if I rearrange the columns, if I make the if I make an arrangement of columns in such a way, as you can see, all are independently computed. So, U 1 corresponds to V 1, U 2 corresponds to V 2, U 3 corresponds to V 3. So, if I shuffle these columns, similarly shuffle the rows of V 1, V 2, V 3 in the same order, still you will get the same matrix F. So, I will shuffle in such a way that sigma 1 is greater than sigma 2 is greater than sigma 3, which means I will take those column vector, those pairing ui and vi, whose singular value. So, sigma 1, this is called as singular values, whose singular value is the maximum here, then the next maximum, then the minimum. So, this is how the singular value decomposition works, and this is how you can see the matrix can be considered as a superpositions of 3 rank 1 matrices. So, you are just summing up 3 rank 1 matrices, each one is a 3 cross 3 matrix. So, now what you can do, that you have to estimate a singular 3 cross 3 matrix which should be very close to your estimated F matrix. Now, that is your computational problem. So, F you have estimated from the data, but that is not singular. So, your objective is to get that solution F prime which would be very close to your estimated F. So, which means you have to minimize the, once again, this is called Frobenius norm. That means, element wise, if you take the square of their differences and add them and take the square root of the sum, that is the Frobenius norm. It is as good as saying that this is L2 norm when you are representing a matrix in the form of a vector by concatenating all its rows or all its columns in whatever way. So, the solution lies in the fact that this would be minimum, that is a theory says that when you set the minimum singular value to 0, that means you are setting to 0. So, you are ignoring this part. So, once you set it 0, now then this F prime is a singular matrix, because that is one of the conditions, one of the signature of a singular matrix, that if you perform singular value decomposition, then at least one of the singular value should be 0. And if I reorder them, all those singular values in order of their increasing values, and as I mentioned that we enforce that singular values should be positive, we can enforce positive or 0. So, the minimum values should be 0 in that set. So, in this case and number of zeros or number of non-zero singular value will also provide us the rank of that matrix. So, since the rank of the of this fundamental matrix is 2, so we are keeping 2 non-zero singular values and only setting the minimum singular value to 0. So, this becomes your solutions now, and you have applied the singular constraint in this fashion. So, this is that we are computing singular value decomposition, and this is the closest rank to approximation from that estimated F matrix. So, one of the nice example that I could get from the book of Hartley and Gisserman, that is multiple view geometry in computer vision, you can see there are the effect of singular F and non-singular F by showing how epipolar lines they behave in a particular image plane. So, this is a right image plane with respect to a left image plane, which is a reference plane, and we are drawing the epipolar lines of all the points, corresponding points of the left image plane in the right image plane. It is expected that all epipolar lines should be converging to a single point, and that is the epipole, that is the right epipole of that stereo system. So, you can see that if it is non-singular, then they are not converging. Only their convergence is ensured if it is a singular. So, that is why geometrically also this property needs to be satisfied, and these are the interpretations and why this constraint is so important in this respect. Now, if I consider the estimation of essential matrix, there is another interesting feature. I told earlier also that number of independent parameters in essential matrix is 5. So, which means there are few more constraints are there. So, let us find out what are those constraints. So, as usual for essential matrix also determinant would be 0. So, just remember essential matrix is the same fundamental matrix when your camera is calibrated, which means you know the calibration matrix of the camera, and you can convert all the image coordinates into the canonical form and express the fundamental matrix just by using the rotation and translation of the world coordinate to camera coordinate system, those parameters. So, extrinsic parameters only. And since there are 6 parameters and also the scale is another constraint. So, there will be 5 independent parameters in this case. So, suppose you have a calibrated camera, that means you know the calibration matrix. So, you can again make that conversions and then you apply the same estimation technique, and whatever fundamental matrix you have estimated, that is essentially an essential matrix, because you get these canonical coordinates and you get in that form of the fundamental matrix. So, there also we need to perform singular value decomposition to enforce the constraint of singularity, but there is one interesting property of essential matrix, that the two singular values that you get here, that should be also equal. So, it is not only that no, there would be only 2 singular values, other would be 0, but the 2 singular values should be the same. So, the way you can enforce is that you consider the average of those 2 values and set them to the sigma 1 and sigma 2 in my previous technique, whatever we discussed. You just make these modifications when you are estimating an essential matrix. Let us discuss now how to estimate fundamental matrix using 7-point correspondences, which is the minimum number that is required, as we mentioned earlier. So, if you have 7-point correspondences, there would be 7 such equations involving the elements of the fundamental matrix, as we also discussed in our previous slides. So, you can see that each row is also formed in the same way what we considered earlier, and there are 7 such row corresponding to each of the 7 pairs of corresponding points. So, now if you would like to solve this, as you can see, this is once again this is a set of homogeneous equations, and since the number of elements in F is 9 and you have 7 equations. So, it is a so the rank of this matrix is 7, and here we can use the singular value decomposition of this matrix A. So, we consider this matrix is A, and if I perform singular value decomposition, then we will be naturally we will be expecting there will be 2 zeros in this case, and the u and v you can consider their dimensions in this form, and v there would be corresponding 0 vectors of this particular matrix A. So, those 0 vectors are the last 2 columns of V, and they can give you the solutions of the equations, because zeros are the solutions of zeros of A are the solutions of these equations, and they are the corresponding fundamental matrix. But since there are 2 such 0 vectors, so actually the solution is a linear combination of these 2 0 vectors. So, we can express the solution as a linear combination of 2 0 vectors f1 and f2 as it is shown here, and this linear combination is given in this form. So, where lambda is any scalar constant, but we have to determine exactly which linear combination, which lambda value, because the fact is that the determinant of this should be equal to 0. It should be a rank deficient matrix, which means if I take the determinant of this matrix f1 plus lambda f2, if I take the determinant, that should be equal to 0. So, as I mentioned, last 2 columns vectors of V would be the 0 vectors, and this is what. Since the determinant, it is not automatically rank 2, you have to solve for lambda, which will give you the 0, and it will be a cubic polynomial because it is a 3 cross 3 matrix, and as you know that in cubic polynomial we would like to get a real valued solutions of lambda, and there are 2 situations, either there will be 1 real valued solutions or there will be 3 such solutions. So, maximum you have 3 such possibilities of fundamental matrices in this case. That is the technique we discussed. So, the essence is that you have to perform singular value decompositions, or rather eigen decomposition of the A transpose A matrix there, and solve for the lambda, which is the coefficient of linear combination of the eigenvectors, by enforcing the determinant of the combination, linear combination should be equal to 0. So, let us consider now the other aspect of fundamental matrix. So, how fundamental matrix can be represented in different parametric form. So, we have already seen how many number of independent parameters should be there, but not necessarily your representation will have that intrinsic characteristics, not necessarily. So, you can represent with more number of parameters, but then you have to enforce the constraints. That means, the dependencies among those parameters needed to be enforced there. So, in the estimation process, this is not always ensured, and post estimation those operations are taken care of, as we discussed, that how we can make the determinant 0 for f. So, over parameterization representation could be in this form. That means, it could be T cross M, where T is a epipole, that is a representation, and there are in this form you see that there are more number of parameters, like you have epipoles T and M. So, M is 9 and T is of 3 cross 1. So, we can write 12 parameters, though we know essentially there are 7 independent parameters. One of the interesting representations which follows this parameterization is this one. You can see that how many independent parameters are there: A, C, E, B, D, F, 6, then alpha and beta. So, there are 8 independent parameters. The interesting part is that the singularity constraint on F, that means the determinant, that is equal to 0 here, because if I take the linear combination of these two columns, the third column is the linear combination of these two columns. So, we know that in this case this is a rank deficient matrix, and one of the column is dependent of others. So, also its determinant should be equal to 0. That is the property of determinant. And if I multiply this f, say with minus alpha, then minus beta and 1, you will find that actually you are getting 0. So, you perform minus alpha A minus beta B plus alpha A beta B, that is 0, and in this way. So, what does it mean? It means that the left epipole, that means 0 of f is this one, so which means it is an epipole. So, alpha and beta has an interpretation in this form, or you can say alpha beta minus 1. So, it is because you are multiplying f e should be equal to 0. So, I think this is fine. So, it should not be right epipole, it should be the left epipole E, this should be this one. Okay. So, let us consider the next one, that is both epipoles as parameters. So, you have this number of parameters A, B, C, D, E, F, alpha, beta. Now, this is another representation. You can see that how many number of parameters you are having here. You have A, B, C, D, then alpha prime, beta prime and alpha and beta. That means, here also you have 8 parameters: A, B, C, D, alpha prime, beta prime and alpha beta. So, A, B, C, D, alpha prime, beta prime, alpha beta. Now, in this case you can find out that if I multiply f with once again with alpha beta minus 1. So, here also you can see that the third column, that means this column, this is a linear combination of first two columns, which is alpha into this and beta into this will give me the third column. And alpha in and also the third row is a linear combination of the first two row, which is alpha prime into first row and beta prime into second row will give me the third row. So, if alpha beta minus 1, that should be equal to 0 like the previous one, and then if I perform on the other way, if I perform the multiplication alpha prime beta prime minus 1 with f, that should be also equal to 0. That means, this becomes your right epipole and this becomes your left epipole. So, in this setup. So, once again now we have the same problem of representation. So, E should be alpha beta minus 1 and E prime should be. So, here also you have a problem. Please note these corrections. E should be alpha beta minus 1 and E prime should be alpha prime beta prime minus 1 as per my diagram. So, let me stop here and we will continue our discussion in the next lecture. Thank you for your listening.